Good evening, everyone. Good eve- good evening, everyone. I welcome you all to the live session six. Sorry, live session number 9 of the course Digital Circuits. So, the course is taught by Professor Shantanu Chattopadhyay of IIT Kharagpur. My name is Mr. Rafiq. I'm the course TA. We carry out this teaching duty as a part of our PMR deliverables. So, hi everyone. I was about to start. Since you have joined, let me reintroduce myself. My name is Musa Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. This is live session number 9. Basically, the live session is the problem solving session. Every week we carry out this session. So initially this session was supposed to be on the Sunday, that is 22nd of September from 3 p.m. to 5 p.m. But due to some unavoidable circumstances, we had to postpone it to 24th of September, that is today. So in today's live session, we'll be carrying out problems pertaining to the memories, semiconductor memories, that is static RAM, DRAM, and most of the problems will be focused on having code problems, finding the correct code, finding the complete code, and also the next week's live session will take place on Sunday, that is I think 29th of September from 3 p.m. to 5 p.m. That is live session number 10. And also one more announcement. Today, my camera is not attached to my laptop, and also due to some bandwidth issues, I am not able to connect my camera. So sorry for that. But I think camera is not that important. We can move forward without that as well. So let's start. Since there is only one student in the live session, and maybe I will not receive any feedback and all, as the attendance is quite low. What I'll do is I'll go through each problem very slowly, and then you can always refer to the recordings that are always available at the YouTube channel that is being shared by the NPTEL team. Right. So let's start with today's live session. As I already announced, that problems will be pertaining to the memories. The problems that we will discuss today are pertaining to the memories, and other than that, most of the problems will be based on the Hamming codes. Right. Let's start with the first problem of today's live session. It's just a simple problem. It states that each cell of a static SRAM cell contains. So the question states that each cell of a static SRAM cell contains. I think it should have been each cell of a SRAM contains, because S is itself static, right? So let's edit that part. Each cell of a SRAM cell contains. Anyone in the audience? How many transistors does a one cell of SRAM contain? You can always type in your answers. Feel free to type in your answers. Just give me a second. Actually, it's pretty dark in here, so each cell of a SRAM cell contains option A, 6 MOS transistors, right? I think you might have gone through the lectures and it's pretty easy. So now I just want to give you a brief idea about this SRAM cell, right? That is a 60 SRAM cell. So for that I have kept some slides here. So this is your circuit diagram of your 60 SRAM cell. The word 60 simply means 6 transistors. You have, let me just tell you that you have other architectures of SRAM as well, that is 80, 90, where your read-write path are decoupled, but let's not go there. We'll just focus on this 60 SRAM cell only. The 6 here stands for 6 transistors, NMOS transistors, or you see here, sorry, not 6 MOS transistors. as you can see, I have labeled them as well. This M1, M2, M3, M4, M5, M6. These are the six MOS transistors that form the SRAM cell. In between, you see this part. Can anyone tell me what is this? If you are comfortable, can anyone tell me the encircle region? What is this? This is nothing but two inverters, cross-coupled inverters. You can imagine it like this. The highlighted portion is simply this. This is basically a cross-coupled inverter which forms the core of the 60 SRAM cell. And your data is stored in the form of Q and Q bar, Q and Q bar, as you can see here. Due to the symmetric nature, see the symmetric nature of SRAM cell. Due to the symmetric nature of SRAM cell, the data is stored in complementary fashion. So if 0 is stored here, here it will be 1. If 0 is stored here, here it will be 1. And also these are termed, these two transistors, M5 and M6, whose gate are connected to the word line. These are termed as access transistors or pass transistors. So this was just a brief overview of the schematic of the 60 SRAM cell. As elucidated, that cross-coupled inverters form the core of 60 SRAM cell. Due to its symmetric nature, data is stored on Q and Q complement in complementary fashion. Storage nodes are connected to the bit lines via access or pass transistors, as I already mentioned. Now, for SRAM, we typically associate three operations. Number one is your hold operation, number two is your read operation, and number three is your write operation. So, in hold operation, your word line is grounded. So, before I proceed to what word line grounded means, in hold operation you neither do read or you neither do what should I say, neither you read nor you do write. So what is done in hold operation, your word line, this line is grounded, so that means word line is connected to ground, that is 0 volts. This was your simply your hold operation. Then the important operation that we have here is read operation. So basically read as itself explains that you need to read the state, what is the value stored, what have you stored in the memory, you need to read that. So let's just explain the read operation here. Suppose q is equal to 1, q equal to 1 is stored, that is q equal to 1, and q bar equal to 0 because of complementary nature. Now we want to read this state, right? So how will we perform the read operation in a 60 SRAM cell? So first of all, what we will do, we will pre-charge these bit line and bit line, this bit line bar and bit line to VDD. We'll pre-charge them to VDD, and then what we will do, we'll assert the word line high. When I say we'll assert the word line high, I simply mean to say we will give VDD to the word line here. Once I give VDD to the word line, which means I'm giving high voltage to the gates of NMOS transistors M5 and M6, which means I'm turning on M5 and M6, right? Now you see this M6 case here, it has VDD from here and VDD from here, so no current will flow here and it will remain as it is. But in case of this, I have VDD on bitline bar and I have 0 here. So a discharging current will flow from M5 to M1 to ground, and as a result there is a discharge on the bitline bar, and hence once there is a discharge on the line bar, I can say that Q bar is equal to 0. That implies Q equal to 1 was stored. So I can sense this using a sense amplifier that will accelerate the speed of the operation. One thing I need to tell you here, sense amplifiers are used to accelerate the speed of the operation of SRAM cell. They are not the necessity, they are just there to increase the speed of operation. So a discharging current will flow from M5 to M1, and this is sensed by the discharge in the bitline bar voltage, and I can say Q bar equal to 0 and Q equal to 1. In this way, I have performed my read operation. Now, after that, I have a write operation. So what is write? Some value was stored and now I need to overwrite it. So since I am dealing with binary, that is simply means I need to flip the values. So initially Q equal to 1 was stored. So Q equal to 1 was stored and now I need to write Q equal to 0. right? So I need to flip its state. So first of all, there is a pre-charge condition. Whatever value you want to store, put that on the corresponding bit line. So I want to put q equal to 0. So what I will do, I'll put bl equal to 0 in pre-charge condition. Pre-charge condition, I'll put bl equal to 0 and bl bar equal to vdd. Now after that, write operation is performed into two stages. In stage 1, word line, again this word line, as you saw in read operation as well, we have the same word line. So that's why I mentioned in 80 and 90 we have the decoupling of read and write word lines. But here we have a common word line for read, write and hold. So in the write operation, what we'll do in first stage, we'll assert the word line hi, that is wl will be put to vdd. And now what will happen, since q equal to 1, q was initially 1 and q bar was equal to 0, and now bit line is equal to 0, right? Bit line is equal to 0, a discharging current will flow from here, and as a result q will tend to discharge. In second phase, that is stage 2, q will be tend to 0. As I said, q will tend to 0, and due to the symmetric nature, because this is connected to the input of this inverter, q bar will tend to 1, and which will in turn flip the q bar, and already q is being discharged. This can be understood from the vtc of the inverter. As v increases, v in, v out decreases. So as q is tending to 0, its output will tend to 1, which is the input of this inverter, which will in turn flip q bar equal to 0. In this way, my write operation is successfully performed. I have not mentioned certain things like we have this cell ratio, pull ratio, or what is cell ratio, pull up ratio. I have not mentioned those things. Those things, if you want to look into those things, you can always refer the book Digital Integrated Circuits by John M. Abai, where those operations are, those things are explained in detail. I didn't want to go into those details. So we have those cell ratio, pull ratio. We want the strength of M1 to be greater than M5, and also we want the strength of M6 to be greater than M4. So we arrive at different sizing problems. I didn't want to touch those things as they were out of the scope of this course. Was this part clear? I just wanted to give this brief overview of the SRAM cell, its read operation, write operation, and hold operation. And by the way, I think it's pretty late to say this, but was I audible? You can confirm in the chat box. Am I audible? Is the screen visible? Just confirm. Was I audible? There's no response, but I think I was. So now let's move forward to question number second. Yeah, first we did that was based on this 60 SRAM cell. Now, which of the following statement is true? Assessing memory location of RAM takes any location of memory RAM takes the amount of time. Assessing any memory location of sequential access memory takes the amount of time. Low cost memories can be designed using SRAM cells. SRAM memories need periodic refreshing rate circuit. So from the options, only statement 1 is correct. Because SRAM memories don't need periodic refreshing, they are volatile memories. Low cost memories can be designed using SRAM cells. Wrong. SRAM cells are one of the costliest memories. They sit at the top of the hierarchy with having high speed of operation and high cost. And also assessing memory location sequence memories takes a amount of time. That is also wrong. Now, question number 3: a programmable logic can be used as a microprocessor. Option B as a dynamic memory. Option C to realize a sequential logic. Option D to realize a compilation logic. I think we have done in the previous week's problem solving session. The correct answer to this is option D, to realize the combinational logic circuit. Now, moving forward, we have this question. The minimum number of transistors required to make a DRAM cell is, so DRAM, when we say DRAM, D stands for dynamic. Dynamic RAM cell is, so the minimum number of transistors required to make a dynamic RAM cell is 1. So we have this 1T 1C architecture DRAM. Here 1T means 1 transistors, 1C mean 1 capacitor. So in the next slide, I'll explain two architectures of DRAM cell, that is 3T1C and 1T1C. Towards the left hand side of the screen is the 3T1C DRAM, and here it is 1T1C. Now let's see the operation of 3T1C. So here you have three NMOS transistors, M1, M2, M3, and you have two word lines, WWL and RWL. WWL stands for your write word line, and RWL stands for read word line. So your read and write paths are decoupled, word lines are decoupled, and you have two bit lines, BL1 and BL2. So let's just first discuss the write operation. So first of all, whatever value you want to store, you want to write, you have to put it on bit line 1. So for 0 you will ground it, and for 1 you will give VDD, you will charge to VDD. Then what we will do, we will assert the WWL high, that is we will give VDD to right word line, which will in turn turn the transistor M1 on. If 0 was stored, this capacitor will be discharged, and if VDD was given to BL precharge to L1, so VDD will be stored at, due to charge sharing, at CS, storage capacitor, that is simply the parasitic capacitor. Now we have to look for the read operation. Write we have already discussed. So for read, we will precharge bit line 2 to VDD. We will precharge this to VDD, and then we will assert the write word line high, that is give VDD to this line. This will turn on M3. Now based on the value on X, it will either turn on M2 or it will either turn off M2. So if 1 was stored here, M2 will be turned on, and as a result discharging current will flow from here bit line, that is M3 M2, and as a result bit line 2 will discharge. If 1 was stored, right? If 1 was stored, it will discharge. But if 0 was stored at X, M2 will turn off and bit line 2 will maintain at VDD. So you see here, when 1 is stored, my bit line 2 will discharge. When 0 was stored, my bit line 2 will be at VDD. So this is a inverting kind of a read operation. Inverting read. Also here sense amplifier is used, but sense amplifier is only used to accelerate the speed of operation. That is not a necessity, right? Now this was all about 3T1C's read-write operation. Now we have 1T1C read-write operation. So here we have this word line connected to the transistor M1. Here we have bit line, and we have this bit line capacitor, and we have the storage capacitor. So for write, whatever value we want to store, we'll put it on bit line capacitor. For 0, we'll ground it, and for 1, we'll give to VDD. And then what, this was a pre-charge phase, and then we will assert the word line high, and due to the charge sharing mechanism, the VDD will be stored on CS, or if 0 was stored on CBL, this will discharge. So this will be either 0 or this will be either 1, that is ground or VDD. Now for read, we'll precharge CBL to VDD by 2. Then we will assert word line high. Once we assert word line high, what we will do, I just write this voltage on CBL here, that is VDD by 2, and here I will perform the read operation. Once I will assert word line high, if CS VDD was stored, due to charge share mechanism, CBL voltage on CBL, this charge on CBL start to increase. And if CS on CS 0 was stored, for due to charge shielding mechanism, voltage on this charge on CBL will start to decrease. So I will have a shift, that is delta V, either up either down. So based on this change in voltage, I can sense whether my 1 was short or 0 was short. Here in 1T1C, just remember sense amp is necessity. It is required. Because this delta V that you saw here, which will increase the voltage on CBL or decrease it, is typically around 100 millivolts. To drive it to the rails, that is to VDD or ground, we need a sense amp. So to push it here or here, we need a sense amp. So here sense amp is a necessity. This was a read-write operation for your 3T1C and your 1T1C. Now let's move forward. So for how many questions we discussed? 4. Yeah. Now we'll discuss question number 5 of today's live session. I think this is pertaining to the Hamming codes. Yeah. So we have this question number 5. It says that find the 12-bit Hamming code for the given 8-bit data word. So we have what we have at our hand is we have given this data, 8-bit data has been given, and we need to find the complete code, Hamming code. So for 8-bit data, 4 parity bits are required, which we label as P1, P2, P3 and P4. So P1 will be here, P2 will be here, P4 will be here and P8 will be here. This is P8 and this is P4. And your data bits will be here D1, D2, D3, D4, D5, D6, D7, D8. Your data is 1010 1100. Now we need to find P1, P2, P4 and P8. So for P1, what we will do, P1 is simply your XOR of data at position 3, data at position 5, data at position 7, data at position 9 and data at position 11. From where do these numbers 3, 5, 7, 9, 11 come from? Basically, if you see your code, let's say P8, P4, P2, P1, you have this 000 0001 0010 0011. So your 1 bits are here, 1 2 3 4, like here, 0 1 2 3 4, whatever position they occupy. So your P1 is the XOR operation of the data bits present at 3 5 7 9 11, that is XOR of 1, because at third position there is 1, at 5th position there is 0, at 7th position there is again 0, at 9th position there is 1, and at 11th position there is 0. So it's XOR of 1 0 0 1 0, that is XOR of 1 and 1, which is 0. Now for P2, I'll have XOR of 3, 4 plus 1 3, 4 plus 2 is 6 6, 3 6 7. 7 is basically 3 7 is basically 4 plus 2 plus 1, so 2 is there, 7. And then there is 10, 8 plus 2, and there is also 11. So data bits present, XOR operation between the data bits present and third position, 6th position, 7th position, 10th position and 11th position. So it is an XOR operation of, at third position it's 1, at 6th position it is 1, at 7th position it is 0, at 10th position it's 1, and at 11th position it's 0. So XOR of 1 1 0 1 0 is simply 1. Then we have P4, that is XOR of 5 6 7 and 12. 4 plus 1, 4 plus 2 plus 1, 4 plus 2, 8 plus 4. So this is XOR of 5 is D2, 6 is D3, that is 1, 7 is D4, that is 0, 12 is 0. So it is XOR of 0 1 0 0, that is 1. And similarly for P8 it is XOR of 9, 10, 11 and 12. So it is XOR of 1 1, that is 1 1 0 0, 1 1 0 0. So it is 0. So I have 0 1 0 0. So I will write my P1 as 0, P2 as 1, P4 as 1 and P8 as 0. So my complete code will be equal to 0 1 1 1 0 1 0 0 1 1 0 0. So that is option if I carefully look, option B. So this was question number 5. If you have any doubts, please let me know. Otherwise, you can progress to question number 6. Now, question number 6, I kept it highlighted it. That means I want you guys to solve it first. Then I'll show the solution. I'll give some time for you guys to solve it. You have just need to type in the correct answer. That is correct option. So the question number 6 states that a 12-bit Hamming code read from a memory location. This Hamming code contains 8-bit data word and a 4-bit code word, just like we saw in the previous question. What was the original 8-bit code word in the memory location if the 12-bit Hamming code is 1101, 0100, 1010? So we have received this 12-bit Hamming code. We need to find out what was the original 8-bit code. So kindly do it and please let me know the answer. Has anyone done it? You can write your correct option in the chat box. So basically you need to find out the, I'll just tell you how to do it. You need to find out the first the error position, at what position the data has flipped, and then write the correct code. So let me just show the solution. If you are doing, please continue to do it. You can always follow the solution later. So you have a 12-bit having code that is released 1101 So you have P1, P2, D1, P4, D3, D2, D3, D4, P8, D5, D6, D7, and D8. So I'll write whatever we have received. I have received 1101, 0100, and 1010. This is what we have received from the memory location. Then I will write C1, that is your XOR operation between 1, 3, 5, 7, 9, 11. That is the XOR at the bit value present at first position, that is 1, third position that is 0, fifth position that is again 0, seventh position that's again 0, then ninth 1, and 11th 1. So XOR between them is 1 1 1 is 1. Then I have C2, that is XOR operation between 2, 3, 6, 7, 10, 11. That is your XOR of 1 0, that is 1 0 1 6, sorry, 6, 1 0 0 1. So XOR of 1 1 1 is 1. Then I have C4, that is XOR of 4 5 6 7 and 12. That is XOR of 4 5 6 7, that is 1 0 1 0 1 0, and 11 12 is 0. So it is XOR of 1 and 1, that is 0. Then I have C8, that is XOR of 8 9 10 11 and 12. That is 0 1 XOR of this thing 0 1 0 1 0. That is 0. So I will write it like this: C8, C4, C2, C1, 0 0 1 1, and the decimal value corresponds to 3. That is, the error is at third bit. So third bit is D1. That was 0, but in correct code it is 1. So my correct code is simply D1, D2, D3, D4, D5, D6, D7, D8. That is 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. That is option A. That is your correct answer. Any doubts, please let me know. If not, we can proceed to the next question. Now, the question number 7 asks us, in Hamming code, how many check bits are required for a data word of 25 bits? So we have a data word like we had earlier, which had 8-bit data word. That is D1, D2, D3, so on up to D8. Now we have D1, D1, so on up to D25. Now for this, how many check bits we need to have it for Hamming code? So for Hamming code, we have this criteria. 2 raised for k should always be greater or equal to n plus k plus 1. K is your number of check bits, n is the number of bits in data word, or you can say simply say data word length. So that implies here, first of all, here n is equal to 25. So that simply implies 2 raised for k should be greater or equal to 25 plus k plus 1. So that implies 2 raised for k should be greater or equal to 25 plus 1 is 26 plus k. So let's put k equal to 5. That implies 2 raised for 5 should be greater or equal to 26 plus 5. That implies 32 is greater or equal to 31. This condition is fulfilled. That implies k is equal to 5. But we also need to check it for 4. But you can clearly see that 2 raised for 4 is 16. That is simply less than 26. So 4 won't work. So the least number of check bits you need is k equal to 5. So that implies option B is your correct answer. Now I have this question. You can try to solve this and then I'll show the solution. It's not that hard. It should only take a couple of minutes. So the question is, what is the size of Hamming code for a 32-bit data word? So now we need to find out the complete size of the Hamming code, where the data word length is 32 bits. Kindly do it, then I'll show the solution after a couple of minutes. I don't see any answers, so yeah, let's not wait that much. So the question asks, what is the size of Hamming code for a 32-bit data word? So we need to find out the complete size. Again, we have this condition for Hamming code. 2 raised for k should be greater or equal to n plus k plus 1. Here n is your 32. That implies 2 raised for k should be greater or equal to 32 plus k plus 1. That implies 2 raised for k should be greater or equal to 33 plus k. So let's just say let's put k equal to 5. That implies 2 raised to power 5 should be greater or equal to 33 plus 5. That implies 32 should be greater or equal to 38. This condition is violated. That implies the next value we'll try is k equal to 6. So 2 raised to power 6 should be greater or equal to 33 plus 6. That implies 64 should be greater or equal to 39. This is fulfilled. That implies k is equal to 6, n is equal to 32. So your total size is equal to 32 plus 6, that is 38. That is option B is your correct answer. This was question number 8. Yeah, this was question number 8. Now I have question number 10. This states that which type of memory has a constraint of minimum operating clock frequency? EEPROM, that is electrically erasable programmable read-only memory. Number 2, static RAM, SRAM. Number 3, dynamic RAM. Number 4, magnetoresistive RAM, that is MARAM. So the only option, correct option here is option 3, dynamic random access, because first of all, why we call it as a dynamic memory? Dynamic means because we need to refresh it after some time. We need to refresh it after some time. So there is constraint on the clock frequency as well. After certain time, we need to refresh it. The dynamic random access memory has a refresh rate associated with it. The refresh operation. Can anyone tell me what exactly is a refresh operation and why do we need it in DRAM? To the audience members, why do we need a refresh operation in DRAM? To those watching the recordings as well, try to answer it before moving forward. Why do we need a dynamic refresh? Why do we need a refresh operation in DRAM? And what exactly is a refresh operation? So let me tell you, this refresh operation is nothing but reading the state and writing the state. And why do we need it? Because the charge stored in the capacitor gets, due to the leaky nature of the transistors, it gets leaked out and then it gets discharged. It has some minimum frequency associated with it, minimum clock, say refresh period associated with it, within which we need to refresh the state. By refreshing the state, what I really mean is I read the state and again write that state. That is simply your dynamic operation, and this is simply your refresh operation, which means reading then writing it again. Now, question number 10. Which memory is difficult to interface with the processor? A. Static memory. B. Dynamic memory. C. ROM. 4. None of these. Again, for this operation, we have the correct answer as dynamic memory, because there are some timing and latency issues. Also, there is a bus complexity involved, and also we need a refreshing cycle that is associated, that is dependent by some minimum clock frequency, as you saw earlier as well. Now we have a question: what is the Hamming distance between the code 11001011 and 14 times 0111? So we need to find out the Hamming distance. My first data is 11001011, and then we have 1000 1. I think it should be 1 1 2 3 4 zeros. Yeah, it's 4 zeros. Yeah, 1 2 3 4 4 zeros. One, uh, 1 1 1. So we need to perform. We need to find out the Hamming distance. So for finding the Hamming distance is simply your Hamming code 1 XOR with code 2. So we will perform an XOR operation. So 1 XOR with 1 is 0, 1 XOR with 1 is 0, 1 XOR with 0 is 1, 1 XOR with 0 is 1. This is 0 0, 1 XOR with 0 is 1, 1 XOR with 1 is 0. So your Hamming distance is simply number of ones performed after number of total number of ones after we perform the XOR operation. So that is 1 plus 1 plus 1, that is 3. So the Hamming distance between them is 3. So this was your question number 11. Now I'll have question number 12 for you to solve first, then I'll show you the solution. It shares that the final code after encoding data bits 1101 into 7-bit even parity Hamming code. So I forgot to tell you that we were following even parity so far, right? So even in this question we follow even parity. That is, you need to do the XOR operation. So the final code after encoding data bits 1101 into 7-bit even parity Hamming code is. So find the complete Hamming code and write down your correct answers. So let's solve it. So we have this 4-bit data word, that is 1101, and we need to find its Hamming code. So we have P1, P2, D1. So it is 1, 2, 3, 4, P4, then D3, D4, D5, D2, D3, D4, that is 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, D1. So now what we'll have here is, we have D1, that is 1, D2, that is 1, D3 0, and D4 1. P1 is simply your XOR operation between D1, 1, 3, 5 and 7. That is the bit values present at third position, fifth position, seventh position. That is 1, 1 and 1. XOR of 1, 1, 1 is 1. Then we have P2, that is XOR of 2 plus 1 is 3, 3, 4 plus 2 is 6 and 7, 3, 6, 7. So it is XOR of 3 is 1, 6 is 0, 7 is 1, it is 1. Then I have P4, that is XOR of 5, 6, 7, that is XOR of, so P2 was 3, 6, 7, right? 3, 3, 6, 7, 1, 0, 1, so this is 0. Again for 5, 6, 7 I have 1, 0, 1, so 1, 0, 1, that is again 0. So that implies P1 is 1, P2 is 0, and P4 is 0. So my complete code is 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. That is option 3. That is your correct answer. Now moving forward to question number 13, which states that SRAM memory offers option A high density, option B lower cost, option C high speed, and option D lower power consumption. Among the following options, only one of them is correct, that is high speed. So if you see this memory hierarchy that is like a pyramid, you have the registers, then you have the SRAM cell. Basically, SRAM cell is present in your cache memories. So they are typically very have low density and are very high costly and have very high speed of operation. So down the pyramid, you have cost that is going down, and going towards the pyramid is your high speed. So this is your SRAM cell that offers high speed. Then a DRAM cell stores the binary information. A, the external capacitor connected to it, the parasitic capacitor of MOS transistor, the external inductor connected to it, and option D, the resistor. It is the option B, that is the parasitic capacitor of the MOS transistor, as we saw earlier as well. Then we have question number 15, which states that DRAM memory offers A, low density, B, low cost, C, high speed, and D, higher power consumption. So DRAM memory offers option B, low cost. It's a low cost memory. It offers high density, it's low cost, has moderate speed, and low power consumption. Then question number 16. Which of the following is not a non-volatile memory? CD-ROM, it is a non-volatile. Magnetic disk, it is a non-volatile. SD card, it is a non-volatile. SRAM cell, as you saw earlier, the moment you turn off the supply voltage, your content is lost. So option D is your correct answer. This was question number 16, which asks us which of the following is not a non-volatile memory. Option A CD-ROM, B magnetic disk, C SD card, option D SRAM. So option D is your correct answer. Then I have question number 17, and just like the previous 2-3 questions that I asked you guys to solve first, I want you guys to solve this first, then I'll show the solution to you. So it states that which of the following is the even parity Hamming code for the binary word 11111111. So you need to find out the complete Hamming code for the data word 111111. Do it, then I'll show the solution. So let's solve it together then. So we have this data word that is 8 bit long, that is 1 1 1 1 1 1 1. So you have D1, D2, D3, D4, D5, D6, D7, D8. One goes here, one goes here, one goes here. So this is and then we have parity bits P1, P2, P4, P8. We need to find these. So P1 is simply as we have done so far as XOR of 3, 5, 7, 9, 11. So as all of them are 1, so it is XOR of 1, 1, 1, 1, 1, 5 ones, that is ones. Then it is XOR of 2, so 3, 6, 7, 10 and 11. That is XOR of 1, 1, 1, 1, 1, 5 ones, that is ones. P4 is XOR of 5, 6, 7, 12. That is XOR of 4 ones, 1, 1, 1, 1, that is 0. And P8 is XOR of 9, 10, 11, 12. That is XOR of 1, 1, 1, 1, that is 0. So I have then P1 as 1, P2 as 1, P4 as 0, P8 as 1. So my complete code will be then 1, 1, 1, 0, 1, 1, 1, 0, then 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1. Option C. So you could have done this question in few seconds. So all the data bits were 1. So in P1 and P2 5 values are taken. So that is 5 ones were XORed. That is 1 1. And P4 and P5 4 at 4 positions the values are XORed. So that means 4 ones were XORed. That is 0 0. So in just 10 or 12 seconds you could have solved it easily. So for question number 17, option C is the correct answer. Then question number 18 asks, a memory unit 1024 cross 64 is specified by the number of word times the number of bits per word. How many address lines are needed for a given memory? So we have a memory that is 1024 cross 64 and you need to find out how many addresses are needed for that. So for this we have the conditions of memory. When we have memory, we expect it like memory unit, we expect it like 2 raised power k cross n, where n is your number of bits per word, and 2 raised power k is your number of words. So here 1024 cross 64 is equal to 2 raised power k cross n. What is this k? This k is simply your number of address lines. That implies 2 raised power k is equal to 1024. That implies k equal to log of 1024 to the base 2. That implies k equal to 10, because 2 raised power 10 is 24. That is option C. Now question number 19. It asks us, in a message transition, suppose that the received Hamming code message is 01110110001. Identify the location of the error bit in the received stream. So we need to find out the position at which the error occurred. So let's just draw 1, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. P1, P2, D1, P4, D2, P3, D4, D8, D5, D6, D7, D8. What did we receive? We received 0011, 1011, and then 0100. So then C1 is XOR of, as we have done earlier so far, 1, 3, 5, 7, 9, 11. That is XOR of 0, 1, 1, 1, 0, 0. XOR of 1, 1, 1, 1 is 1. Then C2 is XOR of 2, 3, 6, 7, 10, 11. That is XOR of, at 2 it's 0, 3 it's 1, 6 it's 0, 7 it's 1, 10 it's 1, and for 11 again it's 0. So it's XOR of 3 ones, that is 1. Then C4 is XOR of 4, 5, 6, 7, and 12. So it is XOR of 4, 5, 6, 7, that is 1, 1, 0, 1, and 12 is 0. It is 0. No, it's 1 because 3 ones are there. Then C8 is XOR of 8, 9, 10, 11, 12. 8, 9, 10, 11, that is 1, 0, 1, 0, 0. That is 0 because 1 XOR with 1 is 0. So my error is at bit position C8, C4, C2, C1, 0, 1, 1, 1. That is 7. That is 7th bit. Error is at bit position 7. That is option C. Now question number 20, that is the last question of today's live problem solving session. What is the length of Hamming code for an even input data worth of length 60 bits? So we have done these types of questions earlier as well. So here that time we said in Hamming code 2 raised power k should always be equal to greater or equal to n plus k plus 1, where k is your number of check bits and n is your number of data bit word length of data bits. So 2 raised power k and n here is 60. That implies 2 raised power k should be greater or equal to 60 plus k plus 1. That implies 2 raised power k should be greater or equal to k plus 61. Let's assume k equal to 7 or 8. Let's assume k equal to 7. 2 raised power 7 should be greater or equal to 7 plus 61. 2 raised power 7 is 128. 128 should be greater or equal to 68. That is correct. So that implies k is equal to 7, n is equal to 60, n plus k, that is total length, is equal to 60 plus 7, that is 67. Option C. So that was all for today's live problem solving session. If you have any doubts throughout this live problem solving session, you can ask me this time. If you want me to relook any problem, please let me know. Since it's only 1 hour 10 minutes, I think we can wait for 5-10 minutes. Otherwise, I'm not going to solve any other problem. If you want to leave, you can leave. If you have any doubts, you can ask. I'll just wait for 5 more minutes. I'll just wait if someone some new participant might join. Then we can pick some problems. Not a new problem, but among these problems. Otherwise, there will be no more problems, new problems solved, and you can leave. If you have doubts, please let me know. And next week we'll meet at our scheduled time, that is 3 p.m. to 5 p.m. on the Sunday. That is 29th of September. I think that time we'll mostly discuss microprocessors, if I'm not mistaken, or maybe something else. I'm not sure right now. So rather than waiting, I can just give a brief overlook. So we have question one. We need to write how many how many transistors are there present in a static RAM cell. So the correct answer was individually that is we talk about 60 SRAM cells. So there are six MOS transistors, as we saw in the schematic here as well. This portion corresponds to your cross-coupled inverter here, which forms the core of 60 SRAM cell. These are your excess transistors or pass transistors. Then we discuss the hold operation where the no write or read operation performed. Your word line is grounded. Then we have the read operation where the word line was exerted high, bit lines were precharged, and then we had, since the state, we had the write operation. We need to flip the states. Then we had this question which of the following statement is true. What can be a PLA used for simply for realizing a combination logic. The minimum number of transistors to make a DRAM cell is 1 in 1T1C structure. We saw two architectures of DRAM cells, that is 3T1C and 1T1C. We also saw that for 3T1C sense amp is not a requirement, but for 1T1C sense amp is a requirement because the total voltage swing that is happening there is only typically around 100 millivolts, and to drive these swing to two rails, that is VDD and ground, you need a sense amp. Then we saw these Hamming codes problems. Any doubts? Someone raised a hand. If there are any doubts, please let me know. I guess it was by mistake. Anyways, you can always ask doubts. So we need to find the Hamming code, 12-bit Hamming code for a given 8-bit data word. So 1010 was your Hamming code. Then we use this thing to find the parity bits, and finally the code was 12-bit Hamming code was found. Similarly, here we had the received Hamming code, and we need to find out what was the correct uh, code that was stored. What we did, we found the where was the error location, we corrected it, and then we wrote the correct answer. Also, these were some of the questions where we need to find out how many check bits are required, what is the total size of a Hamming code. Again, like this, the condition is 2 raised power k should be greater or equal to n plus k plus 1, where n is your data word length and k is your check bits. So these are some of the simple questions. This is again finding the Hamming distance between two codes, simply performing the XOR operation, then counting the number of ones, which is the Hamming distance. This is again finding the Hamming code for a 4-bit data word. So for 4-bit data word, we need only three parity bits, that is P1, P2, P4. Then we have SRAM memory offers, that is the high speed. It sits at the top of the memory hierarchy. DRAM cells store binary information on the parasitic capacitor. DRAM memory cell offers low cost. Which of the following is not a non-volatile memory? It is your SRAM, which is a volatile memory. Again, a Hamming code problem. This is your finding the number of address lines from the memory unit. This is the message transmission was given, and we need to find out the error location. And again, the Hamming code problem we had. So I think it's 1 hour 15 minutes. I don't think anyone else will join, and we have covered 20 problems. That is sufficient. I thank you all for joining this live session number 9 of the course Digital Circuits. We'll meet next time on 29th of September. We'll discuss question, problems pertaining to week 10 material. I think we are left with now 3 live sessions, that is 10, 11, and 12. And there will be one more live session, that is the recap live session, that I think will be of 1 hour. That will be at the end of the semester. We'll let you know about that. So thank you guys for joining. See you next time.